We have already seen the maximum modulus principle for holomorphic functions. It's stated that if f is a function which is defined on a domain omega, and if k is a compact subset of omega, then the supremum of the absolute value of f in k is attained on the boundary of k. In this lecture, we will be giving a phenomenal application of the maximum modulus principle in proving the very famous Schwarz's lemma. And thereafter, we will give a characterization of the automorphisms of the unit disk. Automorphisms are functions, holomorphic functions from the unit disk to itself, which has a holomorphic inverse. So we will get to all that. Let me begin this lecture by recalling the maximum modulus principle for you. Recall that the maximum modulus principle states that if f from omega to c be a holomorphic function on an open set omega contained in C, and K be a compact subset of omega, then the absolute value of f of z is less than or equal to the supremum of z in the boundary of K of f of z, absolute value of f of z. This is true for all z in K. So this is the exact statement of the maximum modulus principle which we had proved. Let me now focus and bring your attention to the very special unit disk. In this lecture, we will mostly be dealing with omega to be the unit disk. And let's start with, so let me just state the Schwarz's lemma, and we will describe what the lemma says after we write the statement of the Schwarz's lemma. So to do that, let f from D to D be a holomorphic function. Let it be a holomorphic function which fixes the origin such that f of 0 is equal to 0. That's all. With just this set of assumptions in the hypothesis, we can conclude that absolute value of f of z is less than or equal to mod z for all z in D, and the absolute value of the derivative of f at 0 is less than or equal to 1. Furthermore, if f of z, absolute value of f of z is equal to the absolute value of z for some z in D, or if the absolute value of f prime of 0 is equal to 1, then there exists lambda in C with absolute value equal to 1 on the unit circle, such that f of z is equal to lambda z. So let's now just go over the statement and see what it says. Notice that f is a function from the unit disk to itself which fixes the origin. That's the only hypothesis that is imposed on f. And we get to conclude that f of z is then having absolute value less than or equal to z. So in other words, every point is sent closer to the origin. Geometrically speaking, that is what this particular theorem says. Schwarz's lemma says that every point in the unit disk is sent closer to the origin. If that is not happening, if for some point in the unit disk absolute value of f of z is the same as the absolute value of z, then it's a rotation. Notice that lambda times z is just a rotation when lambda is of absolute value 1. When lambda is of absolute value 1, it means that lambda is some e to the power I theta. Multiplication by e to the power I theta is just a rotation. Let's give a proof of this particular theorem. It's actually a quite straightforward application of the maximum modulus principle. So to see how maximum modulus principle comes into the story, since f of 0 is equal to 0, we have g of z equal to f of z by z has removable singularity at 0. Or you could, in fact, you could get hold of the explicit power series expansion of g by considering the power series expansion of f of z. So this has a removable singularity, and hence g can be now thought of as a function defined on the unit disk. Now let's focus on a smaller disk contained in the unit disk. Let 0 less than r be less than 1, and on D0R. This is a smaller disk whose closure is a compact subset of the unit disk. And by applying the maximum modulus principle on the function g, which is now defined on the unit disk, by applying, not on d, rather, let me just rephrase it, by the maximum modulus principle on D0R bar applied to G, we have the absolute value of G of Z is less than or equal to the supremum of the absolute value of f of Z for Z mod Z equal to small r divided by mod Z, which is equal to r. This is true for all Z in D0R. And we know that since the function f takes the unit disk to itself, mod f of z is certainly less than or equal to 1. So this is less than or equal to 1 by r. And that is true for all z in D0R. This inequality is true for all r less than 1. For all 0 r less than 1, let's take limit as r goes to 1 from values lesser than 1. So taking limit as r goes to 1, we have the absolute value of g of z is less than or equal to 1 for all z in D01. This is precisely what we, in fact, this is true for all D0R, but when we take the limit, we can conclude that this is true for all z in D01. But what is the meaning of mod g of z less than or equal to 1? I.e., absolute value of f of z by mod z is less than or equal to 1. That's precisely what it means, which translates to saying that f of z is less than or equal to 1, is less than or equal to absolute value of z for all z in D01. Oh, notice that this is actually true only for D01 minus 0. What is going to be g of 0? Notice that g of 0 for all z in D01 minus 0, right? This is precisely what it says. Anyway, for 0 also we know that f of 0 is equal to 0, so there is nothing to, maybe I shouldn't unnecessarily add these restrictions here, but we still have something else to prove. We have to prove that mod f prime at 0 is also less than or equal to 1. Also notice that f prime at 0 is just equal to g of 0, and we just noted that g of 0 is less than or equal to 1, and since g absolute value of g of 0 is less than or equal to 1, which implies in particular that f prime at 0 is also less than or equal to 1. So we have established both the conclusions that we were trying to establish here. But then there is something more which we have to look at. What happens when this inequality is not strict? In other words, what happens if indeed g of z is attaining its maximum? In the proof of the maximum modulus principle, we have in fact proved that if the maximum is attained in some interior point of k, then the function f is identically equal to a constant along with the identity theorem. So let me just state that, and notice that if absolute value of g of z is equal to 1 for some z in the unit disk, then g is a constant function, i.e. g of z is equal to lambda for all z in D and for some lambda such that absolute value of lambda is equal to 1. But that translates to saying that i.e. f of z is equal to lambda times z for all z in D, including the point z is equal to 0. So the maximum modulus principle, the strong version rather, tells us that if you have the function satisfying the condition that absolute value of f of z is equal to the absolute value of z for z not equal to 0 for some z in D minus 0. Let me just add that, because if D is equal to 0 z is equal to 0 is also allowed, this is always going to be satisfied. So the theorem is true when z is D minus 0, and for at the point 0 is captured in f prime of 0. Both are in fact just reverse engineering the fact that our function g that we defined here, this has absolute value 1. So this is also the case when absolute value of g of 0, similarly if g of 0 is equal to 1, this is the case when f prime of 0 has absolute value equal to 1, then yet again in some interior point the maximum is being achieved and hence g is a constant. Let me just directly write that f of z is equal to lambda times z for all z in D, and some lambda such that absolute value of lambda is equal to 1. So that completes the proof of the Schwarz's lemma. Let's now look at very specific functions. Before we go any further, let's look at some very special functions of the unit disk to itself. So let's consider the following function phi subscript a from D to C given by, may not use this, let me use alpha here. So for alpha in the unit disk, define phi a to be the following function, or rather phi alpha to be the following function. Phi alpha of z, this is equal by definition to z minus alpha by 1 minus alpha bar z. Notice that this is a Mobius transformation which vanishes at 1 by, which has a pole at 1 by alpha bar, but because alpha is in the unit disk, alpha bar is also in the unit disk, and 1 by alpha bar is going to be in the complement of D bar. So this function phi alpha is in fact defined and is holomorphic in a neighborhood of the closure of the unit disk. We will focus on phi alpha from D to C. That is where we will focus our attention to, even though this is defined everywhere on C minus 1 by alpha bar. Why are we looking at this particular function? We can very immediately define phi minus alpha of z and check that this, if you compose with phi alpha of z, what is this going to be? Phi minus alpha is just defined analogously, and that's going to be equal to z plus alpha by 1 plus alpha bar z. That is precisely phi minus alpha of z, and we are composing it with phi alpha. So this is going to be z minus alpha by 1 minus alpha bar times z plus alpha by 1 plus alpha bar z. This is precisely the composition, and a very quick computation will tell us that this is by 1 plus alpha bar z minus alpha bar z plus minus absolute value of alpha square. And if you notice, this is just going to be equal to 1 minus absolute value of alpha square times z by 1 minus absolute value of alpha square, and that's equal to z. So phi minus alpha is an inverse of phi alpha. Similarly, phi alpha, so they are inverses, they are functions which are inverse of each other in wherever we can talk about phi alpha, phi minus alpha of z. Of course, phi minus alpha is also a Mobius transformation. And one more key thing to note is that phi alpha of, if you pick a point on the unit circle, let's see what happens to the absolute value there. That's going to be equal to e to the power I theta. What was phi alpha? Just have a look, z minus alpha by 1 minus alpha bar z. So this is going to be e to the power I theta minus alpha by 1 minus alpha bar times e to the power I theta, the absolute value of this. And some manipulations will tell us that this is absolute value of e to the power I theta minus alpha by the absolute value of e to the power I theta when taken out as a common term. Then I will have to introduce an e to the power I theta here minus, or rather e to the power minus I theta minus alpha bar. This is precisely what we have. This is going to be equal to the absolute value of w by the absolute value of w bar, which is equal to 1, where w is just equal to e to the power I theta minus alpha. So what we have established is that absolute value of phi alpha of z is equal to 1 for all z in the boundary of T, the boundary of the unit disk. And by the maximum modulus principle, again, absolute value of phi alpha of z is less than or equal to 1 for all z in D. And clearly this is not a constant function, and therefore this is going to be an open subset of D. And by a very similar argument, phi minus alpha of z is also less than or equal to 1, and it can be shown by using both phi alpha and phi minus alpha that phi alpha of the unit disk is equal to the entire unit disk. That means that phi alpha from D to itself is a holomorphic map of D to itself, which has a holomorphic inverse. And that's precisely what is the definition of an automorphism of a domain omega. So let me just give a definition here. Definition of automorphism. In the context of complex analysis, when we use the word automorphism, we mean a function. We say that a function f from omega to itself is an automorphism if f is holomorphic and has a holomorphic inverse. So in particular, it's going to be bijective as well, and the inverse is also demanded to be a holomorphic function. And if that happens, then our function f is said to be an automorphism or a biholomorphism onto itself. Automorphism is the word that I would like to use, and what we have just checked above is that phi alpha is an automorphism of the unit disk. For alpha in D, for every alpha in D, we can get hold of one automorphism of the unit disk. The phi alpha has some nice properties. For example, phi alpha of alpha, if you notice, this is equal to 0, and phi alpha of 0 is equal to minus of alpha. You can also check that the derivative, you should sit down and check this out, phi alpha prime at 0 at 0 is equal to 1 minus mod alpha square, and the derivative of phi alpha at, not mod, the derivative itself is equal to 1 by 1 minus mod alpha square. So these are all simple checks which I would urge you to sit down and work out the details for. Let's now try to get hold of what are all the automorphisms of the unit disk. We already saw a big class of automorphisms. Let's now try to see what are all the automorphisms of the unit disk. To do that, let's try to answer maximal problem rather. So let's ask the following question. Let f be a map from the unit disk to itself such that f of alpha is equal to beta, where alpha and beta are points in the unit disk. Where alpha and beta are points in the unit disk. So the question that we would ask is, what is the maximum possible value of f prime at alpha? So what is the maximum value of f prime at alpha when we arrange the supremum over all possible functions f from D to itself, which maps alpha to beta, where alpha and beta are two fixed points. So what is happening? What we are asking for, what is the supremum of mod of f prime of alpha, where the supremum is taken over this particular family. This is precisely what and f of alpha equal to beta. Notice that we have just, I didn't put the condition of holomorphicity here, but we are dealing with holomorphic functions, and the only condition other than holomorphicity is that alpha is being taken to beta. That's the only condition. Now let's try to answer this particular question, and the first thing to remember is that phi alpha of alpha is 0 and phi minus alpha of 0 is going to be equal to alpha. Both are things which we should be using very crucially here, because if you compose f composed with phi minus alpha, then phi minus alpha will take 0 to alpha and f will take alpha to beta, and if you compose further with phi beta, beta is going to be mapped to 0. So if you consider the function, define g of z to be equal to phi beta composed with f composed with phi minus alpha of z, then g is a holomorphic function because it's a composition of holomorphic functions. G is a function which maps D to itself because all these three functions map D to itself, and g of 0 is equal to 0. Now that's the final requirement to apply our Schwarz's lemma, and Schwarz's lemma in particular tells us that then the absolute value of g prime of, maybe I should have called it f, but f was already used, absolute value of g prime is less than or equal to 1 by the Schwarz's lemma applied to g. But what does that mean? What is g prime of 0? G prime of 0 is just equal to phi beta prime by chain rule. What was g, by the way? G was phi beta composed with f composed with phi minus alpha. So this is going to be phi beta prime evaluated at f of phi minus alpha of 0, which is exactly beta. If you notice, 0 is mapped to alpha and alpha is mapped to beta by f. So this is phi beta prime at beta times f prime at phi minus alpha of 0, which is equal to alpha times phi minus alpha prime at 0. This is precisely what we will have by the chain rule. Check that. This is what happens by the chain rule. So if you now focus on the absolute value of g prime at 0, that's going to be the product of the absolute value of these three numbers. We know what is phi beta prime of beta, that is equal to 1 minus 1 by, that is equal to 1 by 1 minus mod beta square. So let me write this as 1 minus 1 by 1 minus mod beta square. This is already a positive quantity, so because beta is in the unit disk, so this is already positive, so the absolute value is not needed, times f prime at alpha times what is phi prime, absolute value of phi prime of phi minus alpha prime of 0. That was computed to be equal to 1 minus mod alpha square. And we know that this is less than or equal to 1 by the Schwarz's lemma, which tells us that the absolute value of f prime at alpha is going to be less than or equal to 1 minus mod beta square by 1 minus mod alpha square. This is the upper bound of what f prime of alpha can have in terms of absolute value. Any function from d to d such that f of alpha is equal to beta is taken, we have the absolute value of f prime at alpha is less than or equal to 1 minus beta square by 1 minus alpha square, 1 minus mod alpha square. And let's see what happens if this equality happens. If equality is attained here, what do we know? We then know that g of z is equal to, so as a digression, if g prime of 0 has absolute value equal to 1, this would tell us that g of z is equal to some lambda times z for lambda on the unit circle. That means that phi minus beta, or rather phi beta composed with f composed with phi alpha of z, see phi minus alpha of z is going to be equal to lambda times z. And by manipulating this, which tells us that f of z is going to be equal to, let's first look at lambda times phi alpha of z. That's what will give us phi minus alpha of phi alpha of z, which is z, and then we'll compose from the left by phi minus beta. So this is precisely what we will get if g prime at 0 is equal to 1. And notice that phi alpha is a map from the unit disk to itself, multiplication by lambda is just a rotation, and hence it's a map from the unit disk to itself. Phi minus beta is also going to be a map from the unit disk to itself. So this function f of z, so define, so consider f from unit disk to itself given by f of z is equal to phi minus beta lambda phi alpha of z. So if you consider this particular function f of z, which is given by phi minus beta lambda phi alpha of z, this is a function which maps alpha to beta, and the absolute value of f prime at alpha, this is equal to the maximum, which is given by 1 minus mod beta square by 1 minus mod alpha square. So the maximum value that can be attained is hence equal to 1 minus mod beta square by 1 minus mod alpha square. So why did we go through this question of this maximality question about what is the maximum value that can be attained? The reason is that this is going to give us an answer on how to characterize all possible automorphisms of the unit disk. Let me write down a theorem. Let f from D to itself be an automorphism. Then there exists alpha in the unit disk and lambda in the boundary such that f of z is equal to lambda times phi alpha of z. So the theorem tells us that any automorphism of the unit disk should necessarily be of this type. So let's see how that's going to work out. We have done all the hard work to prove this result. The proof is now going to be a few lines, just a few lines. The first thing to notice is that f being an automorphism will have a pre-image of 0. Let alpha in D be such that f of alpha is equal to 0. Remember that f is an automorphism. So in particular, it's going to be injective and there is only one such alpha. Now because it's an automorphism, let G from D to itself be the holomorphic function, which is the inverse, such that g of f of z is equal to z for z in D. Now what do we have by the chain rule? By the chain rule, at the point 0, at the point alpha rather, by chain rule we have, let me write down what chain rule will give us directly. G prime at f of alpha, which is 0, which is g prime at 0, times f prime at alpha. This is equal to the derivative at the point alpha. Doesn't matter because it's going to be the constant function 1. So this is precisely what we have. But we know that the functions f and g can have a maximum of the derivative at the point alpha, isn't it? We know by our previous discussion, that g prime at 0, this can have an absolute value less than or equal to, let's just go up and check what we had concluded. F prime is going to be less than or equal to 1 minus mod beta square by 1 minus mod alpha square. So if you write it down carefully, what is alpha and beta here? Alpha is 0 here and beta is alpha here. So this is going to be equal to 1 minus mod alpha square by 1 minus 0, which is 1. So this is precisely the bound that we will be getting. And what about f prime at alpha? If you notice, alpha is alpha here and beta is 0. So this is less than or equal to 1 minus beta square, which is 1 minus 0, and divided by 1 minus mod alpha square. So what do we have? Which tells us that absolute value of g prime of 0 times f prime at alpha, this is less than or equal to 1. And the equation here by the chain rule tells us that this is equal to 1, and that means that both these inequalities have to be equalities. That's precisely what the chain rule tells us. So in particular, by observing that the inequality in star is an equality, the equality in star is possible only if both the above inequalities are equalities. It's possible only if the above inequalities are equalities. In particular, what do we have? In particular, mod of f prime of alpha, this is equal to 1 minus mod of alpha square, and that is possible only if f of z is equal to, remember that alpha is getting mapped to 0 here, so in particular beta is 0, so phi minus beta is going to be equal to phi 0, which is just the identity, and there is some lambda times phi alpha of z. This is precisely, so since beta equal to 0 implies that phi minus beta is the identity, and that is precisely what we had set out to prove. So by using the maximum modulus principle and the Schwarz's lemma, we have given a characterization of all automorphisms of the unit disk.